So the Nernst equation is actually really important for being able to understand or determine or predict whether transport of a solute or ion is passive or active. So whether you need energy to achieve transferring that ion or solute across the membrane. And the first part of it is the chemical gradient. So you have diffusion moves from high to low concentration. And that concentration gradient is shown as this natural logarithm of the interior solute concentration to the exterior or outside solute concentration. So this tells you what your solute potential, your solute gradient is. Then we add to that your electrical gradient. So you can measure your electrical gradient by measuring the electrical potential inside the cell and measuring the electrical potential outside the cell in the fluid that you're making the measurements. So that's this side here. We would say that for passive transport across the membrane, the electrical gradient, shown as the difference between the interior and exterior electric potential, should be equal to this term relating the concentration gradient. And this is the Nernst equation. So if this equals that, then you're seeing passive transport of a solute or ion. If these are not equal to each other, then there has to be some sort of active transport to force it to occur. And that brings us to passive versus active transport. We have three primary types of transmembrane proteins involved in transport across the cell membrane. That was a bit redundant. We have channel proteins. Channel proteins are fairly simple. They're just a pore, a conduit through the membrane. So for example, things that are highly polar have a bit of trouble getting through membranes because the interior of the membrane is highly unpolar or nonpolar. These lipid tails. So you have a channel through the membrane, and you can increase the rate of transport of whatever solute. These are very much like aquaporins, which work for water. You can have carrier proteins. These are also passive. They don't require energy, but they're they help the ion or solute across the membrane by picking it up on one side and physically delivering it to the other side. And then we have pumps. Pumps are active transport. They generally require an ATPase, and so that they can pump. So notice that in passive, the transport is along the electropotential gradient. With active transport, it's against the electrochemical gradient. So they need to use energy to overcome the physics. Really quite clever of them. So for this active transport, it comes in about 4 steps. You have these transmembrane proteins, and then ATP is broken into ADP and phosphorus. That phosphorus binds to the protein. As soon as that phosphorus binds to the protein changes shape and allows the proton to fit into a spot. Once the proton binds with the protein, with the protein, it changes shape again and allows the proton to escape on the other side of the membrane. Once the proton has left its little pocket on the membrane, then the membrane changes shape one more time and the phosphorus is released to be made back to be combined again with ADP.